Welcome back, everybody. Sorry I couldn't be there today, but I'm sure that Miss Besky, if this is third period, or Mrs. Wright, if this is fourth period, is doing a great job of taking care of you guys. Today we're going to talk about our very last concept, which is angular velocity. It is a velocity, which means we're going to talk about distance or displacement traveled divided by time. But remember, we're working in circles. So the equation you'll have to keep in mind as we go through this is that the circumference of a circle is equal to the diameter times pi. Or as we've seen it in class lately, 2 pi r, because 2 times r is just the diameter. Often you won't know the diameter or the circumference right out, but you'll know the radius. So you can use the radius times 2 pi to tell us the circumference. Since something is traveling in a circle, circumference is the distance or displacement that something has traveled. If you keep that in mind, you'll be just fine. Now, things that turn, and by turn we mean rotate, have both a linear velocity and an angular velocity. And the linear velocity we've seen already, that v. Remember, v equals 2 pi r over t. That's the linear velocity, that's tangent to the path. What we want to talk about today is the angular velocity. Now, angular velocity is important because it measures how quickly something rotates. But instead of measuring it in meters per second or kilometers an hour or anything like that, angular velocity measures rotation in percent of a circle completed over unit time. It doesn't use percent. The most common use is either radians per second, so we'll talk about radians, we'll review those in just a second. Or we can also see it in RPM, like you have in your car. Linear velocity is distance over time. I don't know why this particular PowerPoint uses S for distance, but whatever, distance over time. We know that one. What we're looking at is down below. Angular velocity is turns per time. So angular velocity is represented by this funny looking W thing right here. That's actually the Greek letter omega. You draw it like this. It's kind of like a W that's gone all curvy like. And on top we have theta, representing an angle. Example of linear velocity, things we've seen before, miles per hour, feet per second, centimeters per minute, etc. Angular velocity will be in part of a circle over time. So for instance, in RPMs, you could have 6 revolutions per minute. Something could go around 360 degrees in one day, like the Earth spins. 2 pi radians per hour, and we'll review radians in just a second. Now, you don't have to know the derivation of this formula. I put it here in case anyone's interested, and also it would be a lot of effort to take it out of this PowerPoint. So, this is what we're interested in right here. This formula relates linear velocity, which is the v, here's our linear velocity, with omega, our angular velocity, using just the radius. So if you know one of these, you know the other one. Now, another word for angular velocity is rotational velocity. It's just a change in angle, how far you've gone along the angle divided by time. And if we're not using RPMs, revolutions per minute, or revolutions per second, or whatever's dictated by the question, we use radians per second. Now, in case you don't remember from geometry, one complete circle, or 360 degrees, is equal to 2 pi radians. And radians are usually called just RAD, or rad. 360 degrees is 2 pi radians. So if something goes around a whole circle, it has gone 2 pi radians. That would be our change in angle. If it's gone around half a circle, it would be pi radians, etc. Just to review, still, just to review, remember, linear velocity, or v, is not our velocity on a curved path. It's a tangent. It's a vector. It's a straight path. And it goes off tangent to the circle. I've got a cool demo that we'll do on I'll see if I can upload a video of it. Seems unlikely, but we'll definitely do it in class on Monday because it's pretty fun. Or I guess Monday's the test. Sorry, we'll do it on Tuesday. Some terms to keep in mind when you're reading word problems about this. The center of the circle is sometimes called the axis of rotation. So if something is orbiting at 5 meters away from the axis of rotation, that means they're 5 meters away from the center, or they have a radius of 5. It's just a different way of saying it. Now, fortunately for you guys, we're not doing any spinning objects. So we're not rotating. We are revolving. We're moving around an outside point. So don't worry so much about the rotation part. Here's an example. Find the angular velocity in RPM, or revolutions per minute, of a microwave turntable if it turns through an angle of 36 degrees each second. Well, omega equals change in angle, d theta, over time. And we know from the problem that that's 36 degrees, there's our d omega, each second, there's our time. So we have 36 degrees for every 1 second. We want to change this into revolutions per minute. So we have to change degrees into revolutions, or degrees into full circles, and seconds into minutes. I'll do the degrees one first. If we want to know a revolution is a full circle. So I'm only going 36 degrees right now. But I know that there are 360 degrees in 1 revolution. So right now my units cancel, and now I've converted things into revolutions. 36 degrees is 1/10 of a revolution. Now I'm going to do the time. I have 1 second. There are 60 seconds in 1 minute. My units cancel. So when I look at this, to find my RPM, do 36 times 60 divided by 360, or 6 would be my final answer right there, I believe. 6 RPM, which I'm not going to write because it's hard to zoom in on this right here. And my units would look sloppy and they'd be difficult to read. But our answer is 6 RPM for this particular problem. The cable lifting a garage door turns around a pulley at a rate of 20 centimeters a second. How long will it take to lift the door 2.2 meters? Now at first this may seem like an angular velocity problem because the cable is, after all, going around a pulley, and a pulley is a circle. But this is why pictures are important. If we have our rope going around a pulley, we see that it's really just moving tangent to the circle. It's not moving in a circle at all. And so this is actually a linear velocity problem. We're going to take 2.2 meters, that's the distance traveled, and use our conversion factor of 20 centimeters per second to convert this into time. So we have 2.2 meters. We know that 1 meter is 100 centimeters, and we know that 20 centimeters take 1 second to go by. So we crunch those numbers and we get 11 seconds. That's how long it takes the door to go up. So on Edmodo there's some practice problems posted for angular velocity and for circular motion in general. They are extra credit. That's right, I said that, extra credit. Each one counts as a full homework assignment. There are 2 papers, you do both of them, you get full 100s for both of them, assuming you get it all right. Now they can't hurt you, I'm only adding them in. right here. If you don't want to do them, you don't have to do them. I know you have other stuff on your plate, but you've got 5 days before the test. It seems like it might be useful to practice more, do better on the test, and earn some of those extra credit points. Things to remember: one full revolution, one full circle, is 2 pi radians. So if we're talking about radians, one circle is 2 pi. And the circumference is diameter times pi, or 2 pi r. If you remember those things and be careful with your problems, I think you'll do just fine. Now, if this is third period, remember Mrs. Wakamoto is available to answer your questions. But don't go over there unless you've actually tried the problem first. She's not your sub. She has other things to do during her off period. However, if you've tried the problem, you've worked it out, you've drawn your picture, your neighbors can't help you, and you can't find anyone else in the class who can help you out, then it's totally acceptable for groups of 1 or 2 to walk over to Mrs. Wakamoto and have her explain the problem to you. If this is fourth period, Mrs. Wright should be able to answer your questions. I think you'll do just fine. Good luck studying for the test, everybody, and I'll see you all when I get back.